You are listening to Nighttime Documentaries. Hi there, tonight we are going to talk about suns, stars that light up the universe. Space unfolds in a deep calm, stretching out unhurriedly, a vast stage where light takes years, centuries, or even millennia to travel from one point to another. Amidst this silent immensity, there are bodies that radiate energy in a constant, predictable, and harmonious manner, maintaining a delicate balance for millions or billions of years. These bodies are suns, active stars that transform matter into light and heat, illuminating entire systems with almost infinite regularity and, without resorting to explosions or violent disturbances, maintaining the continuity of cosmic life and the stability of their environment. And although from a distance the suns appear silent and constant, each one is a dynamic system in which invisible forces balance each other, matter is transformed into energy, and light is born in its core to travel for years without interruption. In this video, we will explore how suns work, how they maintain their balance, how their size, temperature, and chemical composition determine their behavior, and how, amid the vastness of the universe, each star tells its own luminous story. When we look at the sun from Earth, everything seems simple. A bright sphere in the sky, always in the same place, marking the days and the seasons. It gives the impression of something stable, almost motionless. Yet, that calm is only an appearance. In reality, a sun is one of the most active and complex systems in the universe, sustained not by stillness but by a constant balance between opposing forces. From an astrophysical point of view, a sun is neither solid nor static. It is a vast sphere of extremely hot gas, composed mainly of hydrogen and helium. All of this material is held together by gravity, which relentlessly pulls every particle toward the center. Yet, at the same time, from that very center, a force emerges that constantly seeks to expand it. The fact that the sun neither collapses nor disperses is the result of a perfect balance between these opposing tendencies. Gravity acts like a continuous inward embrace. Each layer of the sun exerts pressure on the next, compressing the gas increasingly as it approaches the core. This compression does not happen suddenly but gradually and persistently. As the material concentrates at the center, pressure rises, and with it, temperature. In the solar core, these conditions reach extremes that defy any ordinary human experience. It is there, in that invisible heart, where the sun's true engine begins. Under millions of degrees of heat and overwhelming pressure, hydrogen atoms move at incredible speeds. Normally, these nuclei repel each other due to their electric charge, like two magnets of the same pole. But in the sun's core, gravity has compressed the material so intensely that this repulsion is no longer an insurmountable obstacle. When two hydrogen nuclei manage to come close enough, nuclear fusion occurs. It is not an explosion nor a violent reaction. It is a smooth, almost silent transformation in which the nuclei combine to form helium. Each of these reactions releases a minuscule amount of energy, so small that, in isolation, it would seem insignificant. But the sun's core does not carry out just one reaction. It performs unimaginable numbers of them, second after second, without pause. In our sun, millions of tons of hydrogen are converted into helium every second. And a tiny fraction of that mass is transformed directly into energy, following the profound mass-energy relationship that governs the universe. This constant conversion is the sun's true pulse. This pulse is neither irregular nor chaotic. It is stable, predictable, and continuous. Like a heart beating unnoticed, sustaining life without drawing attention. Thanks to this process, the sun generates an outward pressure that exactly counteracts the gravitational force trying to collapse it. Neither force dominates completely. Both balance each other, keeping the sun in a stable shape for billions of years. The energy produced in the core does not immediately escape into space. Its journey to the surface is slow, almost meditative. For hundreds of thousands of years, the energy advances just a few centimeters at a time, being absorbed and re-emitted countless times. Later, near the surface, heat is transported through gentle movements of plasma in a continuous cycle of ascent and descent, similar to a deep, rhythmic breath. Finally, that energy reaches the sun's visible surface and is released into space as light and heat. The light we see today may have begun its journey when the first humans did not yet exist. Even so, it reaches us steadily, without interruption, illuminating the Earth day after day with astonishing regularity. This continuous flow is what distinguishes active suns from the more violent phenomena of the cosmos. There are no sudden collapses or unpredictable outbursts here. Everything happens rhythmically, orderly, almost elegantly. Even when the balance is slightly disturbed, the sun corrects itself. If the core is compressed more than usual, fusion accelerates and pressure rises, pushing outward. If pressure drops, fusion slows, allowing gravity to regain control. The system self-regulates naturally. Our sun has maintained this balance for approximately 4.5 billion years. And it will continue to do so for several billion more. Other suns, with different masses, experience this same process over shorter or longer time scales, but they all share the same fundamental logic, a stability that does not arise from rest, but from constant, perfectly synchronized internal activity. Understanding this completely changes the way we perceive the sun. It is no longer merely a source of light in the sky, but a dynamic system, silent in appearance yet profoundly active within. And while we observe just one from our small corner of space, there are billions more scattered across the galaxy, repeating the same constant pulse, each in its own way, illuminating the universe unhurriedly and tirelessly. Although it may seem contradictory, the most energetic region of a sun is also the quietest and most serene. In the core, where nuclear fusion converts hydrogen into helium, there is no chaos or violence. There exists a precise equilibrium that persists for millions, even billions of years. The pressure is colossal, a result of the weight of all the outer layers compressing the stellar center, and the temperature reaches millions of degrees. In this environment, particles move at extreme speeds, collide, and fuse, releasing energy, yet all occurs within narrow bounds. Each individual reaction is almost insignificant, but the sum of millions of them sustains the sun's luminosity over eons. If the temperature rises, fusion accelerates and pressure grows, balancing gravity. If it decreases, fusion slows and gravity compresses the core again. In this way, the sun regulates its own heart constantly and silently, pulse by pulse, reaction by reaction, generating an uninterrupted flow of energy. This energy begins a long and complex journey through the stellar interior. First, it passes through the radiative zone, where photons scatter, are absorbed, and re-emitted countless times, advancing slowly and gradually, like a murmur spreading through a dense forest. Then it reaches the convective zone, where enormous currents of hot plasma rise and fall, transporting heat in an orderly, rhythmic fashion. Each layer acts in perfect synchrony with the core. Every movement, every transition, is an act of calculated harmony. For thousands or even hundreds of thousands of years, energy makes this journey until it finally reaches the visible surface, the photosphere, a diffuse, luminous boundary where the material becomes transparent, allowing light to escape into space. Though active, this surface behaves steadily. Plasma patterns emerge gently, reflecting internal dynamics, but without disrupting the overall calm. Energy is released continuously, steadily, and orderly, marking the sun's presence in the cosmos without flashes or fanfare. Time, for a sun, has a different dimension. Scales that seem incomprehensible to humans are mere brief moments. During its stable phase, hydrogen in the core gradually transforms into helium, releasing energy in a constant, regulated manner. Internal changes occur slowly, the core becomes denser, elements reorganize, yet the star adjusts without losing equilibrium. Even suns of similar masses may differ slightly in luminosity, surface temperature, or the duration of their active phase due to small initial chemical variations. Each star is a silent record of its origin, a testament to the cloud of gas and dust that formed it, the materials available, and the history of its region of the universe. This chemical heritage does not introduce chaos or unnecessary complexity, it adds diversity and nuance to a fundamentally stable process. Surface temperature is another silent language. Cooler suns radiate reddish light, warm and gentle, releasing energy slowly but consistently. Intermediate ones, like our Sun, emit balanced yellow tones, sufficient to illuminate entire planetary systems for billions of years. Hotter suns radiate white or blue light, reflecting more active cores and faster fusion. Each color is a trace of internal equilibrium, an expression of the regulated energy flowing from the star's heart. Light travels through space as a silent message, carrying information about pressure, temperature, composition, and stability. Luminosity, in turn, reveals the star's true presence. It does not depend on distance or observation point, it is the energy emitted continuously, an orderly flow traversing the universe for millions of years without losing constancy. Smaller suns radiate gently, affecting only their immediate surroundings, while larger ones illuminate entire regions of interstellar space. In all cases, luminosity remains stable thanks to the precise balance between gravity and the internal pressure generated by nuclear fusion. This constant flow does not manifest as isolated flashes or explosions but as a prolonged current of energy, marking the passage of time silently and firmly. The chemistry of each sun adds further nuance. The proportion of hydrogen, helium, and heavier elements influences how energy is transported from the core to the surface, regulates the opacity of stellar material, and smooths the luminous flow. Over time, as hydrogen transforms into helium and heavier elements redistribute, the star adjusts its internal structure without losing stability. Even seemingly small changes in initial composition can translate into subtle variations in luminosity, temperature, and evolution, but always within a framework of regularity that preserves the constancy of emitted light. Meanwhile, the universe continues its dance at different rhythms. Gas clouds collapse, planetary systems emerge and collide, black holes devour matter, and galaxies reorganize, yet suns continue radiating energy steadily. Their stability makes them permanent beacons, reference points sustaining processes dependent on their light and heat, marking cosmic rhythms with serenity. The light they emit not only illuminates but also carries information, revealing internal pressure, temperature, density, and composition of the star, even millions of light-years away. Each sun, from the faintest to the brightest, is a testament to order and patience. Its color, luminosity, and stability are evidence of a profound balance, between pressure and gravity, between temperature and energy, between time and permanence. Suns act as silent narrators, conveying the story of their existence through light while the universe continues evolving around them. The constancy of their emission transforms the cosmos into a continuously illuminated stage, where the diversity of colors and temperatures forms a harmonious, gradual mosaic. From the reddish tones of small suns to the whites and blues of the most massive, each star is a node in the network of light sustaining the calm of the universe. This light neither shouts nor demands attention, it travels patiently, carrying information about processes that have remained stable for times beyond human perception. Each photon escaping the surface is a messenger of balance, of orderly transformation, of deep, sustained time. Even as a sun ages and begins to exhaust its nuclear fuel, changes occur gradually. The transition to final stages is not sudden but a slow adjustment of internal structure, a gentle reorganization marking the passage of time delicately. Brightness may vary, surface temperature may shift slightly, yet the essence of internal balance persists over long periods. The star remains, as long as it can, a constant beacon in the cosmos. Thus, countless active suns continue radiating light and heat, each with its own signature of temperature, color, and luminosity. The galaxy fills with these silent witnesses, maintaining energetic balance and providing stability to the universe. The light from each star tells its story, a tale of transformation, patience, constancy, and order. There are no abrupt flashes or random bursts, only regulated energy flowing from the heart of the core into deep space, sustaining calm and continuity in the cosmos for eons. The universe, then, becomes a stage of sustained light, a canvas of gradual colors, a mosaic of suns that, without haste or violence, reflect the deep equilibrium governing them. Each star is a poem of physics, chemistry, and time, an expression of order amidst the vastness of space. The light they emit, constant and patient, is evidence that at the heart of every sun there exists a silent, profound, and enduring balance, capable of sustaining entire planetary systems and keeping the cosmos illuminated for countless ages. Beyond size and temperature, there is another fundamental quality that defines how a sun manifests in the universe: its luminosity. Unlike apparent brightness, which depends on distance and viewing point, luminosity is an intrinsic property. It speaks of how much energy a star produces continuously and releases into space in all directions. It is, in a sense, the measure of its true presence, of how much it influences its surrounding environment. Luminosity does not arise from a single isolated factor but from the balanced combination of several elements. The size of the sun is one. A larger surface allows more energy to be released at once. Temperature also plays a crucial role, as even small variations can result in significant differences in emitted light. Yet what is truly remarkable is that, while the sun remains in equilibrium, all these factors adjust to each other to produce a stable, sustained emission. Our sun is a clear example of this constancy. Over millions of years, the total energy it emits barely varies. There are no abrupt changes or prolonged interruptions. This regularity has allowed processes dependent on its light to develop continuously, without disruption. From a human perspective, its luminosity seems immutable, almost eternal. Other suns, both smaller and larger, follow the same principle, albeit at different intensities. Each possesses its own luminous signature, a kind of energetic identity that distinguishes it. Some emit only a fraction of the sun's energy, yet do so persistently that over time their influence becomes profound. These low-luminosity suns illuminate their immediate surroundings gently. They do not dominate large regions of space, nor stand out for intensity, but their light remains present for almost inconceivable periods. For billions of years, they slowly bathe their surroundings with constant energy, allowing processes that depend on that light to evolve without hurry. Their influence is measured not by immediate reach but by duration. In contrast, there are suns whose luminosity far exceeds that of the sun. These bodies release enormous amounts of energy every second, illuminating vast regions of interstellar space. Their presence can be felt across immense distances, clearly marking the surroundings. However, even in these cases, the emission is neither chaotic nor erratic. The star adjusts its internal structure to sustain this high level of energy production. Gravity and the pressure generated by nuclear fusion balance precisely, allowing luminosity to remain stable throughout the active phase. It is not chaotic energy expenditure, but a continuous, organized flow. Most importantly, regardless of magnitude, a sun's luminosity does not manifest as isolated flashes or sporadic events. It is a constant current. Energy is produced in the core, travels slowly toward the surface, and is released into space uninterrupted. This regularity allows light to travel millions of years without losing its stable character, crossing enormous distances unaltered. Over time, a sun's luminosity may change, but these changes are extremely gradual. As nuclear fuel transforms, energy production adjusts little by little. From a human scale, these variations are nearly imperceptible. The sun always seems the same, fixed in its role as a constant source of light. In that same state, countless suns are scattered throughout the galaxy. Each contributes its own intensity to the luminous background of the universe. Some do so discreetly, others more strongly, but all help keep the cosmos continuously illuminated. Thus, luminosity is neither a fleeting flash nor a sudden explosion. It is a sustained presence. a calm and persistent way to occupy space with ordered energy. Thanks to this constancy, the universe does not depend on extreme events to shine, but on millions of suns that, silently, keep the light of the cosmos burning. When observed closely, the light emitted by active suns reveals that color is no longer a mere visual detail but a silent key to understanding their interior. It is not an ornament or superficial feature. It is the direct result of a profound equilibrium between temperature, size, and energy produced consistently. Each sun expresses its internal state through the tone of its light, and does so without abrupt changes, steadily and predictably. At the softest end of this spectrum are suns that emit reddish light. This coloration indicates that their surface temperature is relatively lower than other stars, though still extremely high by human standards. In these suns, energy is released slowly. Their brightness does not project over vast distances, but remains constant for extraordinarily long periods. The gentleness of their light is, in fact, a manifestation of prolonged stability. As surface temperature rises, color slowly shifts to orange and then yellow tones. This transition does not occur abruptly but as part of a natural continuity. Many medium-sized suns, including those similar to ours, lie within this range. Yellow light reflects an efficient balance between energy production in the core and its release into space, allowing sustained luminosity over billions of years without large variations. Beyond this point, there are suns with even hotter surfaces. Their light appears bright white or even blue, a clear signal that energy is released more intensely per unit of surface. These suns have highly active cores, where nuclear fusion occurs at an accelerated rate. Yet even in these cases, the process remains orderly. The star maintains its structure thanks to a carefully sustained balance between gravity and pressure generated by energy. What is remarkable about this phenomenon is that a sun's color does not change suddenly. There are no abrupt alternations or rapid transitions. Any chromatic variation occurs extremely slowly, over millions of years, as the sun evolves and its internal conditions adjust gradually. From a close perspective, a sun's light seems immutable, a constant presence that neither startles nor demands attention. Moreover, a sun's color also influences how its energy is distributed through space. Hotter suns emit a larger proportion of energy at shorter wavelengths, while cooler suns emit at longer wavelengths. This technical difference translates simply into color perception but has profound implications for how energy propagates and affects its environment. Thus, the universe is filled with a continuous spectrum of stellar lights. There are no rigid boundaries between one color and another, only smooth, gradual transitions. Each sun occupies its place within this spectrum, adding its own tone to the luminous ensemble without breaking the overall harmony. Over time, this chromatic diversity becomes a quiet way of reading the state of the cosmos. Without dramatic events or abrupt transformations, suns communicate their internal nature through constant light. In this way, space remains evenly and silently illuminated, sustained by countless sources of light that, without hurry or fanfare, reflect the profound equilibrium that governs the universe. Throughout its active life, a sun passes through stages that, although vast, unfold with remarkable regularity. Once it reaches its stable phase, it spends most of its existence in a state of balance that can be described as serene maturity. During this period, energy production remains constant, and the internal structure barely varies in any perceptible way. The age of a sun does not manifest in rapid or visible changes. Unlike other, shorter-lived cosmic phenomena, stellar aging occurs gradually. The core continues transforming hydrogen into helium, and this slow accumulation subtly alters the internal conditions. However, the sun responds by adjusting its equilibrium without significantly affecting its external behavior. During this long stage, luminosity may increase slightly over billions of years, but this increment is so gradual that it is imperceptible on short time scales. The sun continues to shine in the same general way, maintaining an orderly and sustained energy output. Similarly, the surface temperature remains within a stable range. There are no abrupt fluctuations or sudden changes in color. The emitted light retains its constant character, traveling through space as a continuous signal of stability. In many cases, this maturity represents the longest phase in a sun's life. The star spends most of its existence in this state, without hurry or rapid transitions. From a broad perspective, it is a period of prolonged calm. Meanwhile, the sun's surroundings may change. The space around it evolves, other suns are born or reach their own maturity, but the star continues its activity unaffected. Its age advances quietly, integrated into the slow flow of cosmic time. Thus, the age of a sun is not a mark of immediate wear but a gradual accumulation of internal transformations. During its maturity, the sun remains a constant source of light and energy, accompanying the universe with a stable and predictable presence. Within the enormous diversity of active suns populating the universe, there exists a group that stands out not for intensity or rarity, but for quite the opposite. These are stars characterized by stability, predictable behavior, and a way of existing defined by constancy. They are suns similar to ours, stars that can be understood as gentle variations on the same fundamental balance. These stars share key characteristics with the sun: comparable mass, moderate surface temperature, and stable luminosity. Inside, hydrogen fusion occurs in an orderly, sustained manner, maintaining the delicate balance between gravity, which compresses the core, and the energy trying to expand it. This equilibrium is neither fragile nor fleeting but surprisingly enduring. For billions of years, these stars remain in a prolonged stable phase. Their internal structure changes so slowly that, on a human timescale, it appears almost motionless. Energy flows steadily from the core to the surface, then releases into space without interruption or disruption. It is a repetitive, almost monotonous process, yet it is precisely in this repetition that its strength lies. Although grouped under a single category, not all are identical. Some are slightly larger, others slightly smaller. Some shine with a barely warmer tone, others with slightly cooler light. Yet these differences are subtle. They do not alter the star's overall behavior or disrupt its internal equilibrium. Each adjusts its fusion rate and structure to sustain its own stability, always within a shared framework. These small variations are reflected in gentle changes in luminosity or the color of the emitted light. There are no abrupt jumps or sudden transformations. Everything happens gradually, almost imperceptibly. It is as if each star interprets the same melody with slight nuances, always maintaining the basic harmony. Astronomically, many relatively nearby stars are considered solar analogs. Some have a similar age, others are younger and just beginning their long stable phase. Others are older and slowly progressing toward later stages of evolution. Still, as long as they remain in this main active phase, all share a constant energy output and a well-organized structure. On the surfaces of these stars, moderate phenomena can be observed: slightly cooler regions, hotter areas, subtle changes in surface activity. However, these events do not affect the overall equilibrium. They are superficial variations that do not alter the sun's deep functioning. The core continues to fuse hydrogen regularly, and energy continues its path outward without significant interruption. This prolonged stability makes suns similar to ours particularly reliable energy sources within the universe. They do not stand out for extremes or violent behavior. Their importance lies in their regularity. For billions of years, they maintain a constant presence, illuminating their surroundings without haste or abrupt changes. Observing this set of stars, it becomes evident that our sun is neither an exception nor a rarity. It is part of a vast family of calm, persistent suns scattered across the galaxy. Each illuminates its region of space silently, repeating the same basic pattern over and over, as if the universe relies on these stable systems to maintain continuity. Over time, like all stars, these suns will evolve. Their equilibrium will slowly change, giving way to new stages. But during this prolonged phase of stability, they serve as clear examples of how nuclear fusion can remain under control over immense time scales. In this state, they continue emitting light and heat constantly, reminding us that much of the universe is not sustained by extreme events or spectacular explosions but by slow, repetitive, deeply balanced processes operating silently for billions of years. Although each active sun has its own characteristics, they all share a common origin based on the same fundamental physical principles. The diversity observed among them does not arise from distinct processes or chance but from gradual variations in initial conditions such as mass, chemical composition, and the environment in which they formed. In this way, the universe is not a chaotic collection of isolated stars but a coherent, ordered ensemble of suns following the same basic scheme, modulating their features according to slightly different parameters. From the smallest, coolest, and most discrete suns to the largest, brightest, and most vigorous, the central mechanism remains intact. In all of them, gravity draws material toward the core, pressure raises the internal temperature, and nuclear fusion releases energy in a constant, controlled manner. What changes is not the nature of the process but the scale and pace. Some suns operate almost imperceptibly slowly, while others release energy more intensely, yet all follow a pattern of internal stability. This continuity allows suns to be organized into broad categories based on observable properties such as color, luminosity, and size. However, these categories do not represent rigid boundaries. Between one type and another, there are smooth transitions, stars combining characteristics of several classes, occupying intermediate positions within the spectrum of possibilities. There are no interruptions or drastic jumps. Variation unfolds gradually, like a cosmic canvas painted with shades of light and energy. In many cases, two suns may differ slightly in mass and, as a result, display subtly different behaviors over billions of years. One may consume its hydrogen slightly faster, another may emit slightly warmer light, or vary minimally in chemical composition. Although these differences are real and measurable, they do not disrupt the overall harmony. On the contrary, they contribute to a kind of dynamic equilibrium where each star occupies its place within the universal pattern. Gradually, this diversity contributes to a broader, more complex equilibrium in the universe. Suns of different types illuminate different regions, providing energy in varying proportions but always stably. Extremes are not required for the cosmos to function. The sum of countless constant emissions, each modulated by its own mass, temperature, and composition, is enough. Meanwhile, this variety ensures that the universe is populated by suns in different stages of their active life. Some have just reached their stable phase, others have been shining uniformly for billions of years, and some are slowly approaching the end of their active phase. All coexist, forming a continuous network of light that combines temporality and spatiality in silent harmony. Thus, the diversity of suns does not introduce disorder or chaos but a profound, tranquil richness. Each active star contributes its own form of stability, adding to a luminous background maintained without disruption, supported by processes repeated predictably over and over. Taken together, these moderate variations form the foundation of cosmic harmony, a universe populated by different suns, all bound by the same silent dance of energy and balance. Suns do not emerge or exist in conditions of constant chaos. Although they may appear turbulent from the outside, within, they maintain a remarkably stable equilibrium for most of their lives. The nuclear fusion that occurs in their cores is not a disorderly process, but a reaction regulated by forces that balance each other with precision. Gravity, which tends to collapse the star inward, is countered by the pressure generated by the energy released, resulting in a structure that can remain practically unchanged for millions or even billions of years. This state of stability allows a sun to shine steadily, releasing energy continuously without abrupt changes. While minor phenomena such as sunspots, ejections, or slight variations may occur on the surface, the deep internal workings remain firm. Regularity does not imply immobility but a slow and predictable change. Each phase of stellar life unfolds over timescales so vast that, from a human perspective, they seem eternal. During its main phase, a sun lives in sustained structural calm. It consumes its fuel gradually, adjusting its size, temperature, and luminosity with extreme slowness. Nothing in this process demands absolute isolation. In fact, many stars are not alone in space, yet they still maintain the same internal stability. Not all suns exist in isolation. In many cases, active stars form systems where two or more suns orbit a common center. These systems do not necessarily imply violent interactions. When distances and masses are well balanced, the suns can coexist for millions or billions of years without disturbing their internal stability. In a peaceful binary system, each sun maintains its own equilibrium. Nuclear fusion occurs independently in each core, and energy emission continues as usual. The gravitational interaction between the suns primarily affects their orbital motions, not the deep processes that sustain their brightness. Thus, each star continues its evolution as if it were alone, even while sharing space with another. Orbits in these systems are usually wide and regular. The suns move slowly around each other along repetitive paths that change almost imperceptibly over time. As long as the system maintains its balance, there are no collisions or extreme approaches. Everything occurs within a stable and predictable gravitational choreography. The light emitted by each sun overlaps in the surrounding space, creating regions illuminated by more than one constant source. This combination does not alter the nature of the emission. Each star releases energy at its own pace, and the sum of both generates no conflict, only shared and persistent illumination. In many binary systems, the suns may be very similar to each other, although there are configurations where one is larger or more luminous than the other. Even in these cases, both can remain in their main active phase for long periods without significant interference. Orbital equilibrium adds to internal equilibrium, creating stability that operates on multiple levels simultaneously. Over time, these systems become clear examples of how stability does not depend on simplicity. A sun does not need to be alone to maintain its regularity. It can share its environment with another and continue shining with the same constancy. Thus, both isolated suns and peaceful stellar systems demonstrate that order is a fundamental feature of the cosmos. The presence of multiple stars does not necessarily introduce chaos. Instead, it can give rise to a slow and sustained dance, where each sun fulfills its role without disturbing the other, illuminating space continuously and serenely. The separation between active suns in the universe is immense, so vast that it is difficult to imagine in human terms. Yet this enormous distance does not interrupt the steady flow of light each star emits. Each sun shines uninterruptedly, regardless of how far another may be, and the energy it releases projects into space with a regularity independent of its eventual destination. That light can travel for years, centuries, or even millennia before intersecting with another similar luminous source, creating a network of illumination that slowly forms on a cosmic scale. The light departing from a sun's surface does not fade or hasten. It always travels at its characteristic speed, crossing regions of near-absolute vacuum where there are no obstacles or immediate references. During this long journey, the radiation does not lose its structure or stability. The energy released in an orderly manner within the stellar interior retains its identity, carrying the physical imprint of its origin and the moment it was emitted. In this context, distance ceases to be merely a spatial measure and becomes a span of time. Observing the light of a distant sun is equivalent to looking into the past, receiving a signal emitted when the universe was at a different stage. That signal remains constant because the sun that produced it maintains its equilibrium over extremely long periods. The patience of light is, ultimately, a direct reflection of the patience of the stellar process that generates it. Gradually, almost imperceptibly, space fills with temporal layers of illumination. Each region of the universe receives light from different suns at different times, forming a calm superposition of constant emissions that neither cancel nor disturb one another. There is no competition among light sources, only a broad and orderly coexistence, where each ray occupies its place in time and space. Meanwhile, each sun continues its activity unaffected by the distances separating it from the others. Its core continues producing energy steadily, its surface keeps releasing it outward, and the light persists on its silent journey. None of these processes accelerates or halts due to the vastness of space. The immense scale of the universe introduces continuity, not urgency. Over time, this dispersed distribution of active suns ensures that the universe is illuminated evenly on a large scale. There are no regions saturated with energy or zones permanently deprived of light over long intervals. Everything occurs within a broad and sustained equilibrium, maintained by the constancy of countless stars that, without coordinating with one another, contribute to a global stability. Thus, the distance between suns does not disrupt the harmony of the cosmos, it expands it. The light, patient and persistent, connects regions separated by enormous intervals, carrying with it the calm of its stellar origin. In this silent journey, illumination becomes a continuous testament to balance, time, and permanence. When observing the universe on a grand scale, one of the most evident differences between active suns is not their color or immediate brightness, but their size. The mass with which a star is born profoundly shapes its behavior, almost as if it defines its personality from the outset. Although all stars operate under the same fundamental principle, nuclear fusion balanced by gravity, size determines the pace at which this process occurs and the way energy manifests outward. Smaller suns, those with a mass less than that of our Sun, live their existence in a calm and patient manner. Within them, gravity is more moderate, so the pressure and temperature of the core reach levels sufficient to sustain fusion, but without accelerating it. Nuclear reactions proceed gently, one after another, without haste. Hydrogen is transformed into helium slowly, as if time held no importance. This measured rhythm has a remarkable consequence, an extraordinarily long life. Some of these suns can remain stable for tens or even hundreds of billions of years, far exceeding the current age of the universe. They are stars that were born early and, in many cases, will continue shining long after most others have changed form or vanished. The light they emit is soft, less intense than that of larger stars. Their surfaces are cooler, and their glow may seem modest from a distance. But this apparent humility is deceptive. These are not weak stars, but constant ones. Their energy flows so gradually and evenly that it shows barely any perceptible variation even over millions of years. They are like a small yet eternal flame, never extinguished or uncontrolled. At the opposite extreme are the large suns, those born with several times the mass of the sun inside them. Gravity exerts a much stronger force. The core is compressed more intensely, raising temperatures to extreme levels. In this environment, nuclear fusion accelerates dramatically. Hydrogen is consumed at a dizzying rate, releasing enormous amounts of energy in a very short time. The result is an impressive brilliance. These suns illuminate their surroundings with dazzling intensity, bathing vast regions of space in powerful and constant light. From afar, they stand out clearly, dominating visually the areas in which they reside. Their presence transforms the environment, influencing surrounding gas and dust and setting the pace for the systems forming nearby. Despite this intensity, the process remains stable for as long as it lasts. There is no chaos or disorder within. The balance between gravity and the pressure generated by fusion is maintained, albeit at a much faster pace. The star adjusts its internal structure to sustain this high energy output, like an engine designed to run at high revolutions continuously. However, this lifestyle comes at a cost. By consuming its fuel so rapidly, these suns exhaust their stable phase in relatively short periods. Where a small star may shine for hundreds of billions of years, a massive star may spend its entire active life in just a few million. Its existence is intense, luminous, and brief by comparison. Even so, during that limited time, its brilliance is neither erratic nor intermittent. It is firm, sustained, and predictable. For millions of years, these suns maintain their equilibrium, radiating energy without pause, until internal conditions change and the star's story moves into a new stage. This relationship between size, rhythm, and intensity reveals something profound about the suns of the universe. There is no single correct way to shine. Some stars illuminate the cosmos with infinite patience, almost in silence. Others do so with overwhelming force for shorter intervals. Yet all, without exception, share one essential quality: while active, they emit energy in an orderly, constant manner, faithful to their nature, maintaining the delicate balance that defines their existence. Observing different active suns, comparison becomes a gentle tool to understand the immense scales involved. It is not about establishing hierarchies, but appreciating how slight initial differences can give rise to notable variations in size, luminosity, and duration without breaking the fundamental equilibrium. Comparing a small sun with one similar to ours reveals contrasts in brightness and temperature, but also deep similarities in internal functioning. Both maintain nuclear fusion steadily, balance gravity with energetic pressure, and emit light in a stable manner. Similarly, comparing the sun to larger, more luminous stars shows how the same process can operate at a greater scale. The primary difference lies in the speed at which fuel is consumed and in the intensity of emitted light. However, the principle of stability remains intact throughout the active phase. These comparisons help us understand that stellar scales are governed not by abrupt changes, but by continuous gradients. Between one type of sun and another, there exist countless intermediate states, each with its own equilibrium. Over time, these differences translate into varied durations of active life. A small sun may shine for extraordinarily long periods, while a large one does so with greater intensity over less time. Both, however, contribute steadily to illuminating the universe. Meanwhile, these comparisons also help us gauge the energy involved. Even the most modest sun emits amounts of energy that far exceed any human-scale process, and it does so consistently, without apparent effort. Thus, comparing suns is not about highlighting extremes, but recognizing a broad continuity. Each active star occupies a place within an ordered spectrum, contributing its own form of stability to the luminous ensemble of the cosmos. When comparing the sizes of known suns with that of the solar system's sun, it is useful to imagine these differences as smooth enlargements or reductions of a single fundamental model. The sun can be considered a central measure, neither particularly small nor exceptionally large among active stars, a reference point on a vast scale encompassing tiny dwarf suns to dazzling giants. Some suns, very similar to ours, have slightly larger or smaller radii. These differences, while significant in physical terms, do not drastically alter their overall appearance. The star remains a plasma sphere in equilibrium, with a defined surface and constant energy emission. Nuclear fusion occurs in its core with the same orderly rhythm, and the light it emits travels through space steadily, without abrupt changes. Other suns, like Sirius A or Vega, have considerably larger radii. Placed alongside the sun, they would occupy much more space, dominating any direct visual comparison. Their greater size implies a broader surface from which energy is released, explaining their high luminosity and influence on the surrounding environment. Yet, despite their magnitude, they maintain the same basic internal structure: cores where nuclear fusion occurs steadily, pressure and gravity in balance, and surfaces emitting light and heat in a regulated manner. In contrast, smaller suns, such as Proxima Centauri, would be much reduced in size compared to the Sun. Though they appear tiny next to giants like Vega, their internal structure remains essentially the same. Size differences do not eliminate nuclear fusion or internal equilibrium, they only modify the pace at which processes unfold. Energy is released more gradually, and luminosity is lower, but the constancy of emission remains intact. These size scales help us understand that the universe does not favor abrupt extremes, but continuous and graduated variations. Between the smallest and largest suns, countless intermediate sizes exist, each with its own form of stability, each adapting its internal rhythm to its volume and mass. This gradual progression conveys a sense of continuity. Change occurs smoothly from one star to the next, like a natural transition avoiding stark contrasts. Over time, such comparisons help us appreciate stellar diversity without generating shocks. All active suns, regardless of size, share an essential quality: the ability to transform matter into energy in a constant, controlled manner, sustaining the light of the cosmos with serenity and predictability. Thus, by observing named suns and comparing them to the solar system's sun, a deep and tranquil idea is reinforced: the cosmos is filled with stars that, although different in scale, participate in the same silent equilibrium, illuminating the universe steadily and harmoniously, each with its own rhythm, each with its own glow. Within the ensemble of active stars that illuminate the universe, there exist suns whose presence is more discreet, not due to a lack of internal activity, but because of the measured way they release their energy. These smaller suns possess masses below that of the sun and, as a result, develop internal processes that progress with remarkable slowness. Their gravity is sufficient to sustain nuclear fusion, but not intense enough to accelerate fuel consumption, allowing them to live in prolonged calm. In these suns, the core temperature is lower, reducing the rate of fusion reactions. Hydrogen is transformed into helium steadily, but at a much slower pace than in more massive stars. This characteristic allows them to conserve their fuel over extraordinarily long periods, often far exceeding the lifespan of larger, more luminous suns, making them true guardians of cosmic time. The light emitted by these stars is dimmer, with hues leaning towards soft red or orange. Their total luminosity is lower, yet this reduced intensity is compensated by prolonged stability. Over billions of years, these suns remain virtually unchanged, illuminating their immediate surroundings with constancy and without significant fluctuations. Their glow may seem modest, but it is a patient, persistent light capable of traversing space across entire eons without losing its orderly character. Gradually, the energy produced in their core travels outward to the surface following the same principles as in larger stars, albeit at a slower pace. There is no urgency in the process. Each photon moves patiently, passing through layers of plasma that guide it to the exterior. The result is a steady and silent emission, a slow heartbeat sustaining the star's existence. These small suns are often also the most abundant in the galaxy. Their longevity makes them persistent witnesses of cosmic time. While other stars cycle through rapid evolution and consume their fuel swiftly, these suns remain in their active phase for periods that far exceed the current age of the universe. Their stability makes them silent pillars of galactic light, contributing to the continuity and predictability of the cosmos. In this same state, their internal equilibrium is maintained with precision. The pressure generated by nuclear fusion balances gravity stably, without the need for abrupt adjustments. Everything occurs in a self-regulated manner, allowing the star to preserve its structure and energy emission over immense time scales. Their existence demonstrates that constancy can be a powerful form of presence in the universe. In contrast to these small, patient suns, there are stars whose mass and size are considerably greater. These large suns operate under the same basic principles as any active star, but within a context of much stronger forces. Gravity within them compresses material more intensely, raising core temperatures and accelerating nuclear fusion processes. As a result, these suns produce impressively high amounts of energy. Their luminosity is intense, and their light can dominate vast regions of surrounding space. Despite this apparent force, the process remains orderly. The star continuously adjusts its internal structure to sustain this energy rhythm, maintaining a stable equilibrium during its active phase without resorting to explosions or uncontrolled events. The energy generated in the core travels toward the surface more rapidly than in smaller suns, yet without losing regularity. Each stellar layer fulfills its function in transferring energy, allowing light to emerge consistently and continuously. This faster flow reflects the greater intensity of the core but continues to obey the same laws of equilibrium that govern all suns. These large suns typically have high surface temperatures, producing light that is whiter or bluer. This coloration reveals the magnitude of energy per unit of surface, but does not indicate chaos. Nuclear fusion continues in a controlled manner, and the star maintains its shape thanks to a balance between gravity and nuclear pressure adapted to its larger size. However, this equilibrium comes at a cost. Fuel is consumed faster compared to smaller stars. Although these suns shine powerfully, their active phase is shorter in cosmic terms. Even so, during that time, their behavior is stable and predictable, without extreme fluctuations or violent events. Their energy spreads widely, affecting the interstellar environment and shaping nearby regions. In many cases, these large suns act as intense beacons over a defined period, providing high luminosity to vast sectors of the galaxy. Though their active life is brief, their energetic contribution is considerable and sustained while it lasts. The intensity and reach of their light contrast with the patience of smaller suns, yet both types participate in the same fundamental principle of ordered equilibrium. Thus, both small and large suns represent different forms of stellar harmony. Some do so through extreme patience, releasing energy with nearly infinite calm, others through controlled intensity, dominating their surroundings for a shorter period. Within this same framework, both types of stars continue to illuminate the universe steadily, reminding us that stellar diversity does not break general harmony, but gradually, silently, and deeply expands it. As observations of the sky became more precise, some active suns began to receive names that distinguish them within the vast ensemble of stars. These names do not imply any fundamental difference in their functioning, but rather serve to recognize suns that, due to their relative proximity or particular characteristics, have been studied in greater detail. Still, all of them share the same principle of stability that defines active stars, releasing energy steadily and following the same laws of nuclear fusion balanced by gravity. Our Sun serves as a natural reference point. Its size, mass, and luminosity are used as units of comparison to describe other suns. It is a G2V spectral type sun, neither too large nor too small, and its stable behavior has allowed life to thrive in the system that orbits it. The constancy of its light and warmth provides a tangible example of how a sun maintains its balance over billions of years, transforming hydrogen into helium without abrupt changes. Alpha Centauri A, part of the closest stellar system to ours, is a sun very similar to our own. Its mass is just slightly greater, about 10% more than the Sun's, and its luminosity is slightly higher. Its surface temperature, around 5,790 Kelvin, makes it just a bit warmer than our Sun. Nuclear fusion occurs with the same efficiency, and its stable phase extends over billions of years. A curiosity, Alpha Centauri A emits enough light to illuminate nearby planets, although no habitable worlds have yet been confirmed in its orbit. Its companion, Alpha Centauri B, is a smaller and cooler sun, with about 90% of the Sun's mass. Its surface temperature hovers around 5,260 Kelvin, and its luminosity is lower, approximately 50% that of the Sun. This means that although it shines steadily, it does so with a softer light, potentially prolonging its active life longer than Alpha Centauri A. The gravitational interaction between the two creates stable orbits, demonstrating how two suns can coexist without compromising their internal equilibrium. Sirius A is another notable sun. This white-blue star, the brightest in our night sky, has almost twice the Sun's mass and about 25 times its luminosity. Its surface reaches temperatures of roughly 9,940 Kelvin, and nuclear fusion occurs at an accelerated pace, releasing enormous amounts of energy. Despite its intensity, Sirius A remains a stable sun, There are no explosions or chaos within its core. A curiosity, Sirius A has a companion, Sirius B, a white dwarf, which is the remnant of a similar sun that has already exhausted its nuclear fuel. At the opposite extreme is Proxima Centauri, the sun closest to us after Alpha Centauri A and B. Much smaller and less luminous than the sun, it is a red dwarf with a surface temperature of around 3050 Kelvin. Its red, gentle light travels steadily, reflecting the slowness of its nuclear fusion. Its small size and relatively calm activity make Proxima Centauri a long-lived star. It is expected to remain in its active phase for up to 4 trillion years, far exceeding the current age of the universe. Moreover, Proxima Centauri hosts at least one planet in its habitable zone, reminding us that even the most modest suns can influence potentially life-supporting worlds. Arcturus is a red giant, much more evolved than our Sun. Its deep orange light, with surface temperatures around 4290 Kelvin, reveals a sun that has depleted much of its hydrogen and is slowly expanding. Arcturus emits its energy calmly, like a witness of time, and is visible from Earth with the naked eye thanks to its relative proximity of 36 light-years. A curiosity, Arcturus completes its rotation in just about 2 Earth-years, relatively fast for a red giant, indicating it retains some of its youthful angular momentum. In the realm of giants, Betelgeuse stands as an immense, pulsating red supergiant. Its current size could span the orbit of Mars if placed where the Sun is, and its reddish, variable light results from the expansion and contraction of its outer layers. Betelgeuse is in the final chapters of its life, approaching the supernova phase, though the exact timing is uncertain. A fascinating note, astronomers have observed its brightness waxing and waning in cycles, as if it were breathing slowly, a reminder that even giants follow internal rules before their great transformation. Rigel, on the other hand, is a young, powerful blue supergiant. With surface temperatures exceeding 12,000 Kelvin and a luminosity roughly 120,000 times that of the Sun, Rigel burns its fuel at a dizzying pace. Its white-blue light crosses vast regions of the galaxy, and although its active life will be short compared to the Sun, it shines with impressive intensity during that time. Its color and energy contrast with Betelgeuse's serenity, highlighting the diversity of stellar youth and old age. Vega, an A0V-type star, is a white, stable, and precise sun. For centuries it served as a reference point for navigation and the calibration of astronomical instruments. Its luminosity is about 40 times that of the Sun, with a surface temperature of 9,602 Kelvin. Curiously, Vega spins so rapidly that its equator bulges slightly, a phenomenon that does not affect its overall stability, yet gives it unique characteristics in shape and brightness. Altair, near Vega in the constellation Aquila, is a restless sun rotating extremely fast, completing a rotation in less than 9 Earth hours. This speed slightly flattens its poles, and its white light reflects both intensity and tension. Its rapid spin generates minor variations in surface temperature distribution, a reminder that even relatively stable suns can exhibit subtle internal dynamics. Deneb, one of the most luminous supergiants known, emits intense white light from over 2,600 light-years away. Its size and luminosity suggest a mass several tens of times that of the Sun, and though it appears immense from Earth, its light travels calmly through the void, reminding us that physical magnitude does not always imply chaos. Capella is a binary star system composed of 2 yellow giants orbiting one another. Its golden light reflects a shared equilibrium. Both suns contribute to the overall luminosity without disturbing each star's internal stability. It is a small-scale example of stellar cooperation, where 2 suns coexist in harmony. Aldebaran, a red giant in the constellation Taurus, emits warm, deep light. Its relatively cool surface, almost equals 3,900 Kelvin, contrasts with its colossal size, and its glow speaks of age and slow expansion. Observing it is to perceive the patience of the cosmos. Antares, the red heart of Scorpio, rivals Mars in chromatic intensity. It is a supergiant occupying space impressively, if it replaced the Sun, it would extend beyond Mars's orbit. Its mass and expansion remind us that even the general calm of the universe can coexist with giants imposing their presence. Finally, Spica, a blue star in the constellation Virgo, is a nearby binary system. Its two suns interact gravitationally, slightly deforming their shapes. Its bright, elegant light shows how tension and cooperation can produce beauty, even in a stellar environment where colossal forces are at play. Gradually, by learning these suns by name and characteristics, it becomes evident that the solar system's sun is not an exception, but a midpoint in a continuum of stars. Each sun has its own rhythm, color, size, and luminosity, yet all participate in the same stable process that keeps the universe illuminated, reminding us that stellar diversity does not break harmony but enriches it with nuances of time, color, and strength.